Hey everyone, welcome back to the Code Path. I am absolutely thrilled to share today's explainer with you because honestly, we're tackling one of the most fascinating bottlenecks in modern AI. If you've ever built an application using large language models and thought, wow, this is incredibly smart, but it kind of has the memory of a goldfish, well, you are definitely not alone. Today, we're demystifying exactly how AI retains memory using vector infrastructure. We're going to lift the hood and look at the real engineering that allows these models to effectively remember millions of documents. Okay, let's dive into this. Here's our roadmap for the explainer today. We'll be hitting the LLM memory problem, mapping high-dimensional space, core technical mechanics, the database stack, and finally, production realities. Section 1. The LLM memory problem. Let's start right at the core pain point that basically every developer smacks into the second they try to scale an AI application. Look, large language models are brilliant reasoners, right? But they suffer from this severe built-in short-term memory loss. Out of the box, they only know what they were trained on and what you explicitly shove into their prompt, their context window. Now, in theory, you could just copy and paste your entire corporate knowledge base, thousands of PDFs and Slack threads, into the prompt for every single question. But practically, there's just no way. That is financially ruinous and computationally impossible. Context windows are expensive and they're finite. So how do we actually solve this? The industry answer is Retrieval-Augmented Generation, or RAG. I love this definition because it totally cuts through all the academic jargon. RAG essentially fixes LLM memory by stapling a highly specialized search engine directly onto the model. Instead of forcing the LLM to somehow memorize all your private or constantly updating data, RAG acts as the system's external, long-term memory. When a user asks a question, this specialized search engine fetches only the most relevant paragraphs and hands them over to the LLM to read and synthesize.
Section 2. Mapping high-dimensional space.
To understand how that specialized search engine actually finds the right data, we have to bridge the gap between human language and mathematical space. We do this by literally turning words into math through a process called embedding. Let's use a quick Python-friendly analogy. Think of it like mapping fruits on a coordinate system. You might have one axis for sweetness and another for color. Because of their shared traits, apples and pears would sit physically close to each other on this graph. Vector embeddings do the exact same thing for text, but instead of just two axes, they map semantic features across hundreds or even thousands of dimensions. So semantically similar text, even if they don't share any of the exact same words, ends up physically clustered together in this vast multidimensional space. And this brilliantly illustrates the massive scale we are talking about here, 1,536. That is the number of floating point dimensions used in OpenAI's super popular text embedding 3 small model. Just think about that. Every single chunk of text you feed it gets converted into a massive array of 1,536 numbers. It's a spatial representation so wildly complex our brains can't even picture it. But mathematically, it allows the system to pinpoint incredibly nuanced semantic relationships between concepts. Section 3. Core Technical Mechanics. Let's transition from those abstract spatial analogies to the actual nuts and bolts of how a vector search pipeline operates under the hood. The standard RAG pipeline basically always follows these 4 steps. First, you chunk. You take your massive documents and chop them up into small, overlapping passages, usually around 200 to 800 tokens. Second, you embed. You run those chunks through an embedding model to turn them into those high-dimensional vector arrays we just talked about. Third, you retrieve. So when a user asks a query, you embed their question too, and search your database to find the closest matching vectors, the k-nearest neighbors. Finally, you generate. You stuff those retrieved text chunks right into the LLM prompt as context. Step 3 is where the real magic happens, and frankly, it's the entire reason vector databases even exist. Now, you might be wondering, why can't I just use a standard relational SQL database for this? Well, traditional databases use B-tree indexes. And don't get me wrong, they are spectacularly fast at finding exact string matches, integers, or ranges. But they fail completely when you ask them to check spatial proximity across thousands of dimensions simultaneously. Doing that in standard SQL basically requires a full table scan for every single query, which absolutely destroys your latency. Vector search fixes this by using approximate nearest neighbor, or ANN algorithms. They intentionally trade a tiny fraction of accuracy for a massive, and I mean massive, speed boost in finding that spatial proximity. But to find that proximity, you have to measure distance. And listen to me on this. Choosing the wrong distance metric will completely ruin your search relevance. If you use an extension like pgvector in Postgres, you've got 3 main operators: The cosine distance, represented by the KWE operator, measures the angle between vectors, totally ignoring their magnitude. This is the absolute industry standard for modern text embeddings. Then you have L2 Euclidean distance, the KT operator, which measures the straight line distance, ideal if physical magnitude actually matters in your specific dataset. Finally, the inner product, or KH operator, which is computationally cheaper and functionally equivalent to cosine, but only if your vectors are already perfectly normalized. Now, what's really interesting about this slide is how it visualizes the trade-offs in search algorithms. It's plotting the EF parameter, which controls your search depth, required to hit specific target recalls as your data size grows, using a very popular algorithm called HNSW, or Hierarchical Navigable Small World. Notice how that blue line, which represents a 99.9% target recall, just shoots up rapidly as the data size scales. To maintain high accuracy, the algorithm has to search wider and harder. In dense, high-dimensional spaces, greedy traversal algorithms can actually get trapped in what we call local minimums, meaning they just stop searching before finding the true best match. As your data grows, maintaining perfect recall gets computationally heavier and heavier.
Section 4, the database stack. So where does all this crazy vector math actually run? Let's quickly evaluate the database options modern developers are actively using today to build these systems. When you move to build, you generally face 3 paradigms. First up, lightweight prototyping tools like ChromaDB. It relies heavily on in-memory operations and SQLite. It's fantastic for hackathons and datasets under 1 million vectors, but it definitely struggles at multi-tenant scale. Then you have the relational approach, pgvector. Teams absolutely love this because it keeps your standard metadata and your vectors sitting in the exact same row, ensuring full ACID compliance and totally eliminating data synchronization bugs. Finally, you have purpose-built distributed systems like Milvus or cloud-native ones like Pinecone. These bad boys are designed to handle billions of vectors with sub-10 millisecond query latency at massive scale.
Section 5, Production Realities. All right, this is where the rubber meets the road. So the crucial point is that the messy operational truth of taking that clean laptop prototype and shoving it into a heavy production environment is that vector indexes are fragile beasts under heavy write loads. If you're using pgvector in production, building an HNSW index on millions of rows can suddenly consume 10 gigabytes or more of your database's RAM. On top of that, updating that HNSW graph with new vectors requires graph traversals and creates lock contention, which can totally bog down your entire database. If you use the older IVFF flat index instead, your clusters degrade as new data changes the distribution, forcing you to do massive periodic rebuilds. And because pgvector is bound by relational transactional overhead, inserting 10,000 vectors takes almost 15 seconds, compared to a pure in-memory library like Face, which just rips through it in 15 milliseconds. And then you inevitably hit the query planner dilemma. Imagine you want to search for a concept, but only within documents marked published. Do you pre-filter or post-filter? If your database pre-filters, it isolates the published docs first, then searches the vectors. Well, this is incredibly slow if the filter isn't very selective. But if it post-filters, it finds the top 10 vector matches first and then checks if they are published. If only 3 of those 10 are published, you only get 3 results back, totally missing great matches sitting just outside that top 10. Dedicated vector databases like Pinecone or Milvus have adaptive strategies built right in to solve this dynamically. In pgvector, you often have to manually engineer your way around these query planner limitations. Which leaves us with a massive, kind of provocative question for the future of back-end engineering. As vector embeddings become a totally standard data type, just like strings or integers, will the immense memory and compute demands of AI fundamentally break our traditional relational databases? Or will tools like Postgres simply evolve to absorb the load? It's a thrilling space to watch as the infrastructure frantically catches up to the algorithms. If you want to continue exploring the deep technical weeds of machine learning infrastructure and really level up your back-end engineering skills, make sure to subscribe to the Code Path. We have a lot more deep dives coming your way. Thanks so much for joining me on this explainer, and I'll see you in the next one.